Hello ladies and gentlemen, my name is Mitch Cox and I'm from the School of Electrical and Information Engineering at Wits University, otherwise known as the University of the Witwatersrand, in Johannesburg, South Africa. I'm going to be talking about bridging the digital divide with a South African perspective. This talk follows from what my previous two colleagues have spoken about, where you received a bit of background into FSO and structured light. I will start with talking about what the digital divide is, and proceed to talking about how FSO may be a solution, and some interesting work on structured light as they pertain to bridging the digital divide. How many of these logos do you recognize? Probably most. This just goes to show how embedded apps are in our lives, and how we make use of the internet every day. That's not the only thing. The world is getting smarter. Some call this the fourth industrial revolution. Things like self-driving cars, automatic traffic management, 5G connectivity, and maybe even artificially intelligent CCTV systems are probably only the tip of the iceberg of what's to come, provided there's enough internet capacity. Did you know that only 24% of African people use the internet, compared to almost 80% in Europe? This doesn't bode well for a smart future in Africa anytime soon, among several other things I'll talk about later. Africa has about 17% of the world population. This means that about 1 billion people in Africa don't use the internet. If we zoom in a little, we can see that a few countries in Africa, namely South Africa, where I'm from, Nigeria, Morocco, Egypt, and Kenya, have significantly more users than other African countries. Many online services assume good internet connectivity, but this isn't always the case. Moving in further to South Africa, we see that there are areas where there is high population density, but quite a long distance to fibre. This is shown on those red patches on the map, resulting in slow internet connection speeds for the people who live there. You can also see that the average internet connectivity in most of Africa is somewhere probably less than about 6 megabits per second. This is pretty slow compared to first world standards. This presentation aims to provide some explanation as to why this is, and of course some possible solutions in an optics context. First, a history lesson. In around 2001, South Africa got its first undersea optical cable. I remember at the time it became possible to get capped ADSL, and when I think back, I wonder how I managed with 3 gigabytes at 384 kilobits per second. Several years later, the CCOM cable enabled uncapped ADSL lines for people, and a few years after that with the wax cable, fiber to the home became affordable and now is pretty common. Overall, Africa appears to be quite well connected in terms of undersea optical fiber. South Africa, for example, has a total of about 50 terabits per second capacity, and it's not all used yet. The new Equiano cable, which is the world's first space division multiplex undersea fiber, is 100 terabits per second just itself, but it's for Google's exclusive use and doesn't count towards general internet capacity, at least in a direct manner. To put this into perspective, a relatively recent cable between the USA and Portugal called the Maria cable is 160 terabits per second alone. The real issue in Africa is terrestrial connectivity. There's a mismatch between where people live and where there's fiber. You can see in Central Africa there are relatively few fibers compared to the darker red on the plot on the top right, which is population density. The orange lines on the left are existing fiber, and the red lines are fiber under construction. It's quite clear that where there is more fiber, there are more internet users, if you have a look at the bottom right. It seems like the problem is being solved, but the space between fibers is actually really vast, as you'll see soon. In Johannesburg, where I live, connectivity isn't really an issue anymore. My university, with the photo on the bottom left, is situated in Joburg, and you can see there is a higher concentration of fiber in the area. Almost all the suburbs in and around the city have fiber to the home, which is quite affordable, with ubiquitous 4G connectivity and even some 5G. Unfortunately, cities like Johannesburg are the exception. Many people live in rural villages with poor internet connectivity. In South Africa, other infrastructure such as electricity and running water is generally available, but I can't say the same for all African or maybe just developing in general countries. Much of Africa is wild, with long distances between human settlements. This makes installing fiber more challenging in some ways, as there aren't necessarily tar roads to simply bury the fiber along. This is a real photo that was taken a few years ago just behind my university. Lions don't usually roam the streets, but sometimes a television advert requires it to drive the wild point home. The real issue with installing fiber in Africa is that Africa is enormous. As visible in this illustration, all of Europe, China, the USA, and India fit quite neatly into the area of Africa. Think about that for a little. Remember the picture of terrestrial fiber in Africa? Those gaps in Central Africa are almost as wide as entire European countries. A few years ago now, Martin Lavery, Andrew Forbes, and I hosted a small workshop at a game reserve near Johannesburg on tackling Africa's digital divide. We discussed some crazy and some good ideas on how we might use optical technologies for this purpose. But to start, I would like to go over some interesting statistics. South Africa, which is relatively well connected, as you remember, has a last few miles challenge. This image shows the population density as dots where there are at least a few hundred people of the country, with the color representing their distance to the nearest fiber, red being further away. 67% of the population of almost 60 million people are within a kilometer of fiber, and 99% are within 20 kilometers. To get all the so-called anchor sites in the country connected to existing infrastructure, in other words, to connect schools, clinics, and police stations in unconnected areas, it would take another 62,000 kilometers of fiber, and that is if the fiber is laid in a straight line. This isn't typical, and if the fiber were to be laid along roads, it would take about 85,000 kilometers. This is a lot of fiber, and South Africa is already relatively well connected. Given that fiber costs on the order of $100 per meter to install, the cost is huge. If South Africa had no existing infrastructure just for fun, a greenfield installation would require a minimum of 159,000 kilometers of fiber. This is obviously unrealistic, and the routing alone would destroy your connection latency, but it's still interesting. This is probably true of most countries, but mobile networks are great for the access network. In 2015 in South Africa, 99% of our population had access to 2G, which to be blunt is pretty slow and useless for modern web apps today. But by 2018, 99.9% of the population had access to 3G. In 2018, about 86% had 4G or LTE coverage. Smartphone penetration is also quite good, with about 82% of phones being smart 2 years ago. This all seems great. Most people have smartphones and access to 4G, so what is the issue actually? I believe it comes down to two things. Technically, just because your phone has 4G, it doesn't mean the connection to the base station is fast enough to deliver 4G speed to everyone. Secondly, data costs money. Allow me to explain with a short story. A few years ago, Vodacom, one of our large mobile service providers, decided to try to get everyone off the old 2G network, as it's obviously simpler to maintain a 3G network and decommission the 2G one. They went to a village and gave everyone a 3G enabled smartphone and asked them to use them instead of their old Nokia 3210s or whatever they used. They monitored the network usage, and strangely, after about a month, everyone had gone back to their 2G phones. They went back to the community and asked them why. It turns out that because smartphones tend to do a lot in the background, coupled with the fact that it's easy to use data inadvertently, like a YouTube clip jumping to 1080p, they use a lot of data in a somewhat uncontrollable manner. This costs money, and in places where people go over to their neighbors to boil the kettle because they've already used up their free electricity allowance, this is not affordable. The cost of data is one of the leading causes of the digital divide. Internet access costs money, and Africa isn't the richest continent, money-wise at least. If we look at the gross domestic product, or GDP, of the USA, it's about $19 trillion. South Africa's neighboring country, Mozambique, is a meager $12 billion, and South Africa is a decent $350 billion. That's only a little more than Apple's annual turnover. In percent, most African countries have a GDP on the order of less than 1% that of the USA. It's not entirely fair to make this comparison in absolute terms, but if we normalize to population, the average American makes $60,000 per year. A South African earns a tenth of that at around $6,000, and in Mozambique, around $400. That's definitely not enough to pay for fiber to the home or a fancy 5G enabled cell phone. The Human Development Index is another interesting metric to compare countries. It is a measure of people's average life expectancy, their level of education, and their standard of living, which is measured using how much money they have. You might be wondering if the internet can be used to raise a country's Human Development Index. I think so. There are numerous online medical resources, and expert systems such as IBM Watson could be used in future to diagnose common and maybe even rare illnesses in the absence of a local specialist. Robotic surgery is also an emerging technology. There are also numerous online education resources. Some are relatively informal, such as YouTube or blogs or maybe even Wikipedia, and some are more structured, such as edX or Coursera, to name a few. Of course, with global lockdowns and quarantines, there are also online conferences like this one. Importantly, a lot of these resources are free. Lastly, there are plenty of ways to make money using the internet, both formally and informally. I want to talk about this last one in a little more detail, since economic growth naturally brings benefits to the other two. The internet is an economic enabler. I think this probably goes without saying, but to highlight this fact, the ICT sector contributes about 6% of the UK's GDP. There are also many ways of earning money with an internet connection, some of which are irrespective of your geographic location. One could become a viral YouTube vlogger or a graphic designer using open source software on freelancer.com. With self-taught programming skills, someone sitting in a village could create apps for mobile app stores and sell them, or even become an Uber driver. Probably the most accessible ways of making money online is by dropshipping things from countries such as China to wealthy people living in cities around the world. Who's to say that awesome XYZ electronics store on eBay is actually someone living in the middle of nowhere? There are many technologies at our disposal to bridge the digital divide. Subsea fiber is ultimately the backbone of the internet, and it is easy to connect areas that are close to these using fiber. Point-to-point microwave links were historically used for backhaul before the days of fiber, and are still in use today in certain situations. Free space optical technology may provide a retrofit alternative to this, with faster and more reliable fiber installed at a later date. To access network could use radio or optical, and there are some interesting projects in this regard, such as weather balloons and such. By now, many of you have probably heard of StarLink, which could one day be an alternative to many of these technologies. Based on what I've read, it appears that the idea is to have a high-speed 20 gigabit per second mesh network between the satellites in space. Since radio is used to the ground, I guess that only megabits per second speeds would be available to users with reasonable latencies. The sky is the limit, however, and if FSO technology were used to the ground, the speeds could theoretically be much faster than with radio. Radio communication is slow and spectrum congested. Slow is of course relative, but a cutting-edge communications satellite can only sustain several hundred gigabits per second, which isn't really that much for the cost of launching one. Long-range Wi-Fi, as seen in the middle photo, can support a few hundred megabits per second over a few kilometers, and carrier-grade wireless, such as millimeter wave, supports gigabits per second also over a few kilometers. Fiber optic links, on the other hand, can support terabits per second with careful design, and hundreds of gigabits per second relatively easily. Assuming fiber is too expensive to install over these long distances, a possible alternative to radio is free space optical communication. On the left is a South African system that supports 1 gigabit per second over 1.5 kilometers with very high reliability, and on the right is a Russian system that can do 30 gigabits per second over the same distance. FSO has been described as fiber without the fiber. The capacity of an FSO link is straightforward to increase using technology from fiber such as wavelength and polarization division multiplexing. Unfortunately, however, the range is currently quite limited, as atmospheric turbulence is a significant challenge, as you will have seen earlier. This scatterplot shows commercial systems as red stars and a selection of seminal experimental systems as blue diamonds. The best commercial system in terms of speed and range is 5 gigabits per second over 5 kilometers, which is quite a lot better than the competition. It is important to remember that there is a specific link budget, and most systems will go further in clear weather. Weather isn't always clear though, and there isn't a standard way to report range. Some systems are more conservative and assume the worst case, where reliability is the primary concern. Other systems assume range is of primary importance, and so the reliability isn't necessarily 99.9% at long range. There are several commercial systems which can sustain 1 to 30 gigabit per second over ranges up to 5 kilometers, but it appears that 5 kilometers is currently the frontier. I've highlighted the region over 5 kilometers and 5 gigabits per second, where you can see there are no commercial systems at the moment. I believe this region is where we need to focus research and development in order to have FSO solutions that can be used to bridge the digital divide. I'm now going to briefly go over some research highlights in areas of optics and photonics that are helping to push this frontier, both in terms of bit rate and range. As discussed earlier by Abdurrahman, structured light is a relatively new area of research which holds promise for FSO. The top paper is the first demonstration of so-called orbital angular momentum modes for mode division multiplexing. On the left is the fastest transmission to date of about 1 petabit per second over a lab bench, and the furthest MDM communication link in free space is only currently around 260 meters. On the right is an experimental setup of a typical lab experiment for mode division multiplexing, this one being 500 gigabits per second in strong simulated turbulence. We've been working on several different approaches to improving the range of free space optic links, mostly looking at structured light. Here you can see me on the left, with Andrew Forbes' group who's on the right, a few years ago, where I did my PhD. We're working together on several different approaches to increase the range of FSO links. Vector vortex modes are OAM modes with a spatially varying polarization, as you can see on the top right of the slide. Scalar vortex modes are the classic OAM mode, with a uniform polarization as seen on the top left. At the time, there were several papers claiming that vector modes were more robust in atmospheric turbulence than their scalar counterparts, but not much explanation why. I asked the question whether this was the case and did the experiment. You can see the experimental setup here at the bottom, which uses so-called Q plates to generate the modes, and a polarization invariant spatial light modulator setup to simulate the turbulence. This is because spatial light modulators can only modulate light with a horizontal polarization. We found that in all turbulence conditions that we tested, given by the so-called Sterile Ratio, the performance is in fact identical within the error of the experiment. Here we show crosstalk percentage, which is how much of the mode spills over into another mode on average. Crosstalk is obviously not a good thing in a mode division multiplex system. As a result, one should use whichever mode set is most suitable for the application based on the properties of the modes, but not because of their resilience to atmospheric turbulence. Are there structured beams that are indeed more resilient to turbulence though? Let's look at what turbulence actually is. In 1976, Knoll showed that turbulence can be broken down into a weighted sum of different component aberrations in the Zernike basis. The phases of the aberrations are shown here. On the left is tip and tilt, well actually tilt and tip, then defocus, astigmatism, and so on. It is interesting to note that about 90% on average of the effective turbulence is tip and tilt. This is easily compensated for by a simple adaptive optic mirror, not even a deformable mirror. But are there modes that are resilient to this without adaptive optics? If we consider the modes on the left column being OAM and Hermite-Gauss, for the correct detection of these modes, precise alignment is required. The arrows in the center indicate the axis that the mode is resilient on. For example, you can see OAM modes can be rotated without affecting their detection, but any translation due to tip and tilt will cause crosstalk into neighboring OAM modes. The Hermite-Gauss modes, or HG modes, are not resilient to rotation, but they are resilient to tip or tilt, depending on the orientation of the mode. For example, the HG10 mode on the bottom left will still be detected correctly even if it moves left and right. For the higher order modes, we assume the same, However, the HG11 mode, which is symmetrical, and perhaps other symmetrical HG modes too, will not be resilient as far as our hypothesis is concerned. And the results agree with this. Let's consider the bottom row, which is percentage crosstalk from one mode to the other. As before, turbulence causes crosstalk, but if a certain mode experiences less crosstalk in the same turbulence, then it is probably a better choice in an FSO system. If we look at the plot on the bottom left, we see that the HG modes, which are green, from the previous page with the HG11 mode excluded, are significantly more resilient in stronger turbulence than LG modes. When the HG11 mode is included, on the bottom right, the performance of HG and LG bases are essentially identical, which agrees with common understanding. The choice of mode clearly affects the performance of a system. So could we use this difference between modes to our advantage? In this variant of modal diversity, we use identical order modes, in other words modes with the same size and same divergence characteristics, from different bases. Each mode is propagated with the same data but half the intensity when one mode is used. This is to keep the overall intensity the same for comparison. Here I show an LG L equals 2 P equals 1 mode, combined with the Hermite-Gauss 2-2 mode, as they are orthogonal to each other and both have order 4. Modal diversity, as shown by Abdurrahman earlier, uses different size OAM modes, which would certainly experience different turbulence. In this case, however, a diversity gain is not expected according to conventional theory, which doesn't predict a modal dependence to turbulence. The results show that there is indeed a significant diversity gain. The bit error rate is quite bad in general here, but the solid lines representing diversity are clearly below the dotted lines which represent the individual modes. As an aside, we still see HG performing better than LG. In the same turbulence, the larger modes are affected less, as expected, shown by the purple line compared to the yellow line. I have plans to redo this experiment in real atmospheric turbulence in my lab, and I look forward to seeing the result, because a diversity gain without multiple apertures would indeed be quite useful for compact systems. You may have noticed that most of the interesting effects of turbulence I've presented so far relate to tip and tilt. I have one more thing to tell you about that. In this work, we built a 150 meter free space link and measured the movement of the beam at 300 frames per second. On the left is a comet plot of the centroid position over time. Notice that the beam does not really bounce around randomly. On the top left, the centroid positions are shown, connected with blue lines. There is a clear average Gaussian shape as expected. The red lines, here, are arbitrarily placed for illustration, but let's assume that they show the extent of the detector. If the beam wanders over this line, bits will be lost. If the beam stays outside the circle for an extended period of time, a potentially catastrophic loss of data may ensue. The bottom left shows the same position data, but limited to a single axis. If we plot the centroid positions against their previous positions, as shown on the bottom right of this slide, there is a clear correlation. This is important because in a communication system, this leads to what is known as a bursty channel. A common example of a bursty channel is in power line communications. Techniques do exist to deal with this sort of channel, but conventional models do not account for this. As such, protocols, error correction, and DSP designed for fiber or radio, where this effect isn't as significant, are suboptimal. Unfortunately, there are no models for this phenomenon in turbulence. All existing models of beam wander are based on memoryless probability distributions. Another way of looking at this phenomenon is using a run-length distribution. This is simply a histogram of the consecutive number of samples the beam spends inside or outside the circle on the previous slide. In other words, this is a histogram of the length of the fades. The green bars show what is predicted using models that use a memoryless probability distribution. The more samples generated, the longer the slope, but the overall slope shape will not change. In a system with memory or correlation, there may be artifacts in this distribution. For example, the tail shown here. On the left is the run-length distribution of the measured data. There is a clear mismatch to the existing model, which led me to investigate a new modeling approach. I don't have time to go into all the details, but if you're interested, please take a look at the paper on arXiv. Suffice to say, a correlated time series model, such as an autoregressive moving average, happens to be an excellent fit for this if we think of the movement as a correlated random walk, not just a true random walk. Knowledge of the beam's movement with time enables us to do more than just optimize error correction algorithms. Since modal crosstalk is related to the movement of a beam, as made quite clear by the previous research I've shown, the ability to accurately predict its evolution may prove quite valuable. So where to now with structured light free space optics? There isn't a difference between scalar and vector modes. HG modes are more resilient to turbulence than LG or OAM modes, but they would allow for longer range links. Evidence so far indicates that modal diversity does work, which opens up some new areas of research in investigating in existing turbulence theory, but importantly allows for a more compact system with only one aperture. And lastly, Beam Wonder has memory, the knowledge of which will hopefully enable the development of better error correction and signal processing schemes for free space optics. So currently the digital divide is vast for geographic and socio-economic reasons. But by using new technologies and future development of existing systems, I hope that we can turn the digital divide into a digital opportunity. Thank you very much.